To run large language models locally on consumer hardware, you have to operate within a strict physical envelope. An average mobile device can only dissipate about 2 watts of thermal energy before it overheats. Thermal limits are only the first constraint. During the decoding phase, when a model actually generates text, every single parameter must be physically moved from high-bandwidth memory directly into the local SRAM caches on the chip. To output just one single word, the processor must sweep billions of weights across these microscopic data pathways. Because memory bandwidth is fixed, the execution units spend the vast majority of their clock cycles sitting idle. The processor is waiting for data to physically travel across the bus, rather than calculating the mathematics of the network. Adding more raw compute power to the system yields zero performance benefit. A faster processor will simply wait faster, starved by the spatial limitations of the hardware memory architecture. The hardware bottleneck compounds when you examine the software layer. Standard operating systems like Linux and Android are built for multi-tenant fairness. They isolate user applications by abstracting physical RAM into virtual memory. These systems divide memory into 4 kilobyte pages. When a language model attempts to sweep a 16 gigabyte weight matrix through the processor, the hardware's translation look-aside buffer cannot keep up. The continuous collisions with these tiny page boundaries trigger massive translation faults, forcing the CPU to halt execution and rebuild its memory maps. At the same time, the operating system's scheduler is programmed to constantly interrupt the active execution thread to handle network packets or background telemetry. These interruptions purge the local caches, replacing your tensor data with generic system instructions. The countermeasure is to strip away the operating system entirely. By booting a bare metal tensor exokernel, you dedicate the silicon to a single deterministic pipeline. You lock the processor strictly into linear algebra loops with zero multitasking allowed. Software frameworks marketed as agentic operating systems fail to solve this because they sit on top of the kernel's memory translations. True performance optimization demands absolute ownership of the silicon scheduling. To build this exokernel, the processor cores are divided using an asymmetric multiprocessing split. Specific cores are assigned to handle external device input, while the primary core is locked entirely in bare metal execution. This hexadecimal map shows how physical RAM is hard-coded. Kernel text is pinned to the 0x0 block, ring buffers to 0x1 million, and 0x3 million designates the contiguous weight arena. Locking the weights into one uninterrupted block completely bypasses the memory management unit, eliminating page faults. This rigid structure solves the problem of sensory ingestion. When the device's microphone and camera capture real-time audio and video, that data flows directly into the 0x1 million ring buffers without the primary CPU ever touching it. This pipeline operates via asynchronous direct memory access. The external controllers are given hardwired permission to write straight to physical RAM, allowing the CPU to continue calculations without wasting a clock cycle. By physically isolating the core execution threat from the chaotic influx of environmental data, the system achieves zero-jitter deterministic latency. Inside that isolated execution core, all background hardware interrupts are forcefully masked. The chip's only function is executing math within this grid of dense circuitry. Most modern edge chips utilize 128-bit hardware vector registers. Instead of running a loop that processes one piece of data at a time, these registers allow the hardware to execute multiple data commands from a single instruction. A single 128-bit hardware lane splits into 16 discrete 8-bit channels. This allows the processor to load 16 individual integer weights and perform 16 multiplications in the exact same clock cycle. Writing code that operates directly on these hardware vectors, completely bypassing high-level runtime abstractions, yields the maximum theoretical floating point output of the silicon. Taking advantage of those 8-bit channels requires compressing the model parameters. A standard asymmetric approach maps floating point numbers to integers by calculating a scale factor and a discrete integer 0 point. This equation carries a severe computational tax. Multiplying these matrices forces the hardware to calculate the cross-accumulation terms generated by that 0 point. To do this, the processor must drop out of its parallel vector lanes and handle the scalar math sequentially. The optimization is symmetric quantization. By clamping the real value range evenly around 0, the 0 point variable collapses. the cross terms vanish entirely, and the hardware stays locked inside its high-speed integer dot product engines. For weight matrices that still exceed the physical memory budget, singular value decomposition can structurally factorize the dense arrays. By stripping out redundant dimensions, a massive calculation is folded into two slim, highly compressed paths. At the bare metal layer, the boundary between software and hardware disappears. A mathematical formula and the physical utilization of silicon are the exact same thing. This deterministic execution profile translates directly to hard real-time robotics. If an autonomous machine relies on a standard Linux scheduler, a sudden operating system interruption will cause a latency spike during a movement calculation, resulting in a physical collision. On a Tensor exokernel, the robot's sensors are treated exactly like a microphone. LiDAR point clouds and inertial telemetry are streamed via direct memory access straight into the isolated RAM buffers. When the model completes its forward pass, it bypasses standard software drivers entirely. It outputs its command vectors directly through memory-mapped I/O pins, blasting immediate, predictable torque arrays to the physical joints. An autonomous robot's mechanical safety is mathematically guaranteed only when the tensor core schedule is absolutely deterministic. This architecture scales to the furthest frontier of hardware, the classical quantum hybrid loop. Algorithms like the variational quantum eigensolver require rapid feedback between a classical processor and a quantum processing unit. If that feedback runs through cloud networking and Linux PCIe drivers, the delay causes the quantum state to collapse into noise before the calculation resolves. The exokernel treats the quantum computer as a direct hardware extension. By linking the QPU to a memory-mapped CXL bus, the classical processor treats the quantum hardware like an ultra-wide vector register. The moment the quantum hardware measures a state, it triggers a physical electrical pin. This sub-nanosecond signal is caught instantly by a custom assembly interrupt service routine inside the kernel. Because there are no abstraction layers to navigate, the routine modifies the parameter matrices directly in the L1 and L2 caches and flashes the new angles back down the bus. Pushing computation to its absolute limit requires abandoning software abstractions. By executing directly on the bare metal, classical silicon logic can communicate natively with quantum states.